Talking about spectroscopy, it's probably a good idea to start with the simplest atom that we have, which is hydrogen. The universe is full of hydrogen, and when we look at what we shall see is excited hydrogen atoms, and if we look through specific sidelines, we'll be able to see something like this. This is the spectrum of excited hydrogen when essentially some electrons go from higher levels to n equals 2. One of the strongest of these lines is H alpha that you can see here. This is responsible for some of the star-forming regions looking very red and beautiful. And within the optical spectrum, we'll actually be able to find two other lines from the Balmer series in hydrogen. But that is essentially it. For hydrogen in the optical, if we look at any line emission, these are all the lines that exist. There are, of course, many other lines in the hydrogen, such as, for example, in the ultraviolet that we can see here. This is Saturn's aurora. This is actually Lyman alpha emission, ultraviolet in the rest frame. And there's also transitions into the infrared, but in the optical, this is all we would be able to see. The important point, and what we'll be exploring next, is that essentially the quantized nature of emission lines due to quantum mechanics essentially allows us to understand what's going on using very simple quantum physics. And this is the reason why we will focus first on hydrogen atoms or a system that only contains one electron. And we can explore hydrogen with the Bohr atom. And for a very simple system of just an electron at some level n, around some positive charge Z, it doesn't have to be 1, it could be higher than 1, but it's just one electron, then in that case, we have an energy that is, we could call this a binding energy of 13.6 times Z squared in terms of electron volts. This means that each level, if the electron is at a specific energy n, its energy will be negative, this is binding energy, minus 13.6, charge squared over n squared. And specifically, if we really are talking about hydrogen in its neutral state, the energy levels will be given by this. We can also calculate energy transitions by using the Rydberg formula, which was known before we even understood what it meant. And this essentially links the energy levels with the wavelengths of photons that are emitted or absorbed.